Okay, well, I want to welcome you all here to see Adrian Brearley. He sent me a bio so I wouldn't have to make everything up. Um, Adrian received his PhD in Earth Sciences from the University of Manchester in '84. He postdoced at the University of Manchester and then moved to the famed Institute of Meteoritics at the University of New Mexico. They liked him so much there, they elevated him to research professor, and eventually he joined the faculty in the Department of Earth and Planetary Sciences in '98, and he's now a University of New Mexico distinguished professor. He's the director of the Nanomaterials Characterization Facility and associate director of the Center for Microengineered Materials. I'm glad he sent me all that stuff. His research interests center around the application of TEM, transmission electron microscopy, and other microbeam techniques to ferret out the secrets of extraterrestrial materials, mainly. He also studies the environmental impact of nanoparticles on human health. He served on the NASA Stardust mission, preliminary sample analysis team that analyzed samples returned from Comet Wild 2, and is currently a sub-team leader for the mineralogy and petrology analysis team for the Hayabusa 2 mission, which is returning samples from Ryugu next month, if all goes well. We certainly hope it does. I also want to mention that although our current president speculated a few months ago about injecting bleach to cure COVID-19, Adrian co-authored a paper 20 years ago about bleaching chondrules. So I guess great minds think alike. That's the perfect segue to today's talk topic, which is child's play, fun and games with mud and goo in the early solar system. Juliet is here and she will turn off everybody except Adrian for now. And if you have any questions, you can put them on chat. And then if Kevin is around afterwards, he will handle the questions that you may have. Okay, Adrian?
I will handle that.
We have you here. Go ahead.
Thank you very much for that very kind introduction. And I'm glad you mentioned bleach. So a little bizarre title here, but what I'm going to do is lead you through talking about hydrous alteration of meteorites in the early solar system. I'm going to particularly focus on a group of meteorites called the CRchondrites. So that's the mud that I've got over here. And I'm in the second part of my presentation, I'm going to talk about goo being the organic material, the carbonaceous material that is present in Carbonaceouschondrites. So we're going to talk about chondritic meteorites, hydrous alteration, and organic materials. First, I would just like to thank and acknowledge the work of many of my collaborators that are all listed here. I wanted to particularly recognize Dr. Christine Floss and Dr. Frank Staderman, sadly, who have both passed away way before their time, both from Washington University, St. Louis. They were incredible collaborators. I miss them hugely, and they contributed greatly to the work that I'm going to be presenting. I also need to acknowledge some of the facilities that we've used, the Advanced Light Source at Lawrence Berkeley National Labs, and the Canadian Light Source in Saskatoon in Canada, where we did synchrotron work, which I will talk about in the second half of my talk. Funding, we couldn't do any of this without money, and so I have to acknowledge the great generosity of the NASA Cosmochemistry and Emerging World programs, which have really enabled everything that I'm going to talk about today. Okay, well, without further ado, let me outline what I'm going to talk about today so you have a little roadmap for where we're heading. So I'm going to do a little introduction, and that is going to be about water and carbon in the early solar system. And a lot of my focus today is going to be on the Carbonaceouschondrites. And I've got an example of an Xray map over on the right-hand side here, which is one of my favorite meteorites that I'll be talking about a lot, QUE 99177. This is an Antarctic meteorite. And what you need to know at this point is that the chondrules that we find are in green, and I'll talk about this, focus on this. The red is the matrix, and that's going to be a big focus of my talk today. So these are carriers of water and carbon. And one of the things that we're really interested in is identifying pristine carbonaceous chondrites. And these are the meteorites that really most or best record the earliest solar system history of water and carbon. And so that's going to be the big focus of what I'm talking about today. And where is that water and carbon? It's dominantly in the fine grained matrix. And the matrix is really the key to understanding the relationship between water and carbon. So that's all in the red stuff in this X-ray map over on the right-hand side. So I'm going to talk about how we recognize pristine chondrites. I'm going to focus on the CRchondrites because they're really a great group to look at. And looking at the very earliest stages of the interaction of water with the carbonaceous chondrites. So aqueous alteration of pristine chondrites. The relationship between organic material and aqueous alteration, I'm going to focus on that towards the end of my talk, and particularly just show the kinds of things that we're able to do now with what we call coordinated micro and nanoanalytical studies. So we're going to be looking at the response of organic material to aqueous alteration, and then I'm going to wrap up with some conclusions and a little bit about how we can apply these techniques to asteroidal sample return. So that's our roadmap. So let's get on and talk about the details. Why do we care about water and carbon? Well, we know life on Earth requires H2O and organic carbon. So that in itself is a significant motivation. The search for life throughout our solar system and beyond in extrasolar system is driven by the presence of water. And so, for example, if we think about Mars, there's a huge impetus for looking for life on Mars. If we look at Europa over here, and Enceladus, the moon of Saturn, these are all places where there is a significant amount of water. This little graphic at the top shows you that despite its diminutive size, Europa has twice as much water as is available in the entire Earth. So it's really one of the places that's been targeted for exploring for evidence of life in our own solar system. So a big question that we focus on is, what is the source and water of organics for the early Earth, obviously, and other solar system bodies? And there's been multiple papers written discussing this about possible sources. Comets have been one that have been proposed. At present, that looks relatively unlikely based on the deuterium-hydrogen ratios of ices and so on in comets. But asteroidal materials, particularly carbonaceous chondrites, still are potential sources of water and carbon that may have accreted to the early Earth. And so this is an area that is becoming of increasing interest to us. What do we know about water in carbonaceous chondrites? Well, when we look at carbonaceous chondrites, the thing that we see is that primordial water must have been widely available in the early solar system, and particularly during accretion of asteroids. And that record of interaction of these early solar system materials with water is present in a wide range of different carbonaceous chondrite groups. And I'm not going to worry about the details of these letters here, but Ci, Cn, these are different types of carbonaceous chondrites with different types of characteristics. The thing that's so interesting about water is, among many of the things that it can do, it can act as a medium for organic synthesis reactions. For example, formation of amino acids. And so there may be processes that occur on asteroids that involve the synthesis of organic materials from simpler organic molecules. And if we look at the relationship between organic carbon and water, and this plot shows the carbon content of carbonaceous chondrites in weight percent over on the y-axis and water over on the x-axis. And I've just plotted up data, bulk water and carbon data with different chondrite groups. And you can see there is a rough positive correlation between the carbon content and water, suggesting that there may be a genetic relationship between them. And that's something that I'm going to explore a little bit later. So let's talk a little bit more about carbonaceous chondrites and get a little bit more focus. Here's an example, a rather unassuming type of meteorite, very dark, has inclusions of different types of lighter colored objects, which I'll talk about in a minute. This is the Murray CM2 chondrite. To give you a little sense, this is about a golf ball sized stone from the UNM collection. As I said, they are recorders of earlier solar system history of water and organics. And why we really like them is that they are free samples from the asteroid belt. Okay? So they're samples of asteroids. We have these two fabulous missions, which are costing many, many hundreds of millions of dollars to go and bring back samples of asteroids. We have the JAXA Hayabusa 2 mission, which Alan mentioned, which will return samples on the 7th of December to asteroid Ryugu. And then we have the OSIRIS-Rex mission, the NASA mission, to bring back samples from asteroid Bennu, showed down here. And so both of these are the types of asteroids that we think are the sources of meteorites like the Murray CM2 carbonaceous chondrite. Why are they so amazing? Well, they are pristine relics of solar system formation 4.56 gigayears ago. And so they have this incredible record that we can decipher and learn about that earlier stage of the solar system. One thing about these meteorites, when we look at them, is they show variable degrees of hydration. They have been affected by water in different ways. Okay, and I've got a little plot down here, which is an infrared reflectance spectra taken by the Hayabusa 2 spacecraft. And what you can see, there's a little absorption band here, and this is the absorption band for water, telling us that there are hydrous phases on the surface of asteroid Ryugu up here. So the samples that come back will likely tell us directly about hydration processes on carbonaceous asteroids. I mentioned earlier that there are carbonaceous materials. There's a remarkable suite of organic materials in carbonaceouschondrites. They are both soluble and insoluble. Okay, they can be extracted by water or polar solvents, or extracted by very aggressive dissolution of the meteorite. And that's the insoluble component. And that's what I'm going to focus on later in my talk. So this insoluble component is the main organic component that we find in carbonaceous chondrites. It represents about 70% of the carbon. And it is a complex macromolecular carbon, high molecular weight. Let's just back up a little bit and talk a little bit about what a chondrite is. I'm sure many of you know already, but it's always nice to put everybody on the same page. They've been widely dubbed a cosmic conglomerate. And the reason for that is they are a mixture of different materials that formed in different conditions and different times and places in the solar nebula, the protoplanetary disk, during the very earliest stages of the solar system. So they're a mixture of coarse-grained components. We have chondrules, which are the rounded objects, and I should have a chondrule pop up here. I'm sure Alan has talked a great deal about chondrules, one of his favorite subjects. So these are objects that formed at high temperature in the solar nebula. So we have things like calcium, aluminum-rich inclusions, very refractory objects. We have the chondrules, which are the main component of things like the CRchondrites that I'm showing here. And they form by processes like condensation and evaporation and melting. Now, what I'm focusing on in this talk is the matrix. That's everything that's between, well, not everything, but almost everything, that is interstitial to the coarse-grained object. So you can see dark areas in here. Some of these are metal grains, but most of this is matrix. And I say it's the most important because it holds the whole object together. Some people disagree with that, but as we'll see, matrix is a very complex micron to submicron mixture of materials. And I've got a little X-ray map here. This is calcium, magnesium, and sulfur. The chondrules are green because they contain magnesium-rich silicates like olivine and pyroxene. And the matrix, hopefully you can see, is purple. It has iron. It also has magnesium and silicon in it. But I wanted to illustrate that it also contains a relatively high amount of sulfur as well, and is very distinct from the chondrules, lower in magnesium. This material, most of it formed at lower temperature than chondrules, and we'll be exploring some of the complexity of this very fine-grained matrix material. So to put all of this in just a little overall history of carbonaceous chondrites, we have to start off thinking about the pre-solar history of the material that we now see in chondrites. And so this is a wonderful picture of the pillars of creation from the Eagle Nebula, M16. And the pillars these are star-forming regions that contain interstellar grains from stars, silicate and oxide dust, also the ejecta from different kinds of stars. And there's organic matter as well that originated in the interstellar media. And it's in these regions where we have molecular cloud collapse and formation of stars, and they're forming in clusters. And so when we think about our own solar system, we believe that it formed in a cluster of other stars, not just our own. So molecular cloud collapse occurred 4.56 billion years ago, and we formed a protoplanetary disk of dust and gas orbiting around the protosun. This is a wonderful graphic produced by Bill Hartman from the University of Arizona, where we're looking inwards through the disk to the protosun forming in the middle. And so this disk of dust and gas is where processing of our PreSolar material took place. And this is where we have condensation of material, evaporation, and melting. People argue about the lifetime of the solar nebula. I'm going to say from about 0 to 7 million years, but that's something that has been argued about extensively. But that's roughly about the time scale that a disk occurred. The disk dissipated due to accretion, and CAIs and chondrules were all assembled into asteroids, like asteroid Bennu that we're showing here. Once we have all these materials together, this is where we can undergo aqueous alteration, thermal metamorphism, and modification of all these primary components, the CAIs, the chondrules, and the matrix. And we know that this process happened for probably at least 15 million years after CAI formation, and longer in some cases, like the ordinary chondrites, probably up to 60 million years. But what I'm going to be talking about, I would argue, took place probably within the first 5 to 10 million years of accretion of asteroids like Bennu and Ryugu. So this is the focus of what I'm going to be talking about today, the aqueous alteration. When we're talking about alteration of chondrites, we have a petrologic sequence that was devised by Van Schmussenwood many, many years ago. And they suggested that if we take the most pristine material that formed in the solar nebula, we're going to designate that type 3. And this is the unaltered material. I'm going to use the term most pristine. Then any process that we do to type 3 chondrites modifies it. So if we interact that material with aqueous fluids and undergo aqueous alteration, it's going to migrate downwards as the primary materials are modified and turned into secondary phases like phyllosilicates, carbonates. And as we get more altered, we go down from 2, and 1 would be completely altered. And so we end up with things like the Murchison CRchondrite, very famous carbonaceous chondrite, which we consider to be a type 2. This process occurs by interaction of fluids, probably melting of accreted water ice. On the other hand, if we heat by, for example, decay of aluminum-26, short-lived radioisotope, the rocks can undergo thermal metamorphism. I've just shown them the idea that we have increasing temperatures, recrystallization, loss of water. I am focusing on type 3s and the very early stages of them turning into type 2s. So these are meteorites that are the most pristine that we have in our collections. And I'm focusing on the CRchondrite group, that are among the most pristine of all the chondrites that we have and are widely considered to be very primitive. I've got a little picture here of the Renazzo CR2 chondrite. The R in CR is Renazzo, it's the type meteorite. We see the chondrules, we see the matrix. But the CRchondrites have experienced aqueous alteration. Most of them are type 2s. There are very rare what we call type 1s that are fully altered, which I'm not going to talk about today at all. I'm just going to focus on the type 2s, and we're going to focus on the idea that these meteorites really have the best record of early solar nebula and asteroidal processes, and teasing that record out is one of the challenges that we're trying to meet. And that's what I'm going to focus on today. When we try to classify a meteorite and decide how pristine it is, most of what we've done in the past is the classification is based on the textures and compositions of coarse-grained phases in chondrules. And I've got a chondrule over here. This is what we call a type 2A chondrule from a CRchondrite. And we can see olivines. There are these clear grains. This is a plain polarized light image. And I hope you can see that between them is a green colored material. And this is pristine, unaltered, quenched silicate glass that formed at high temperature and is very reactive responsive to interaction with fluids. But the glass is very pristine, it's preserved. And so this is an example of what we call a very pristine chondrite. And so a criteria that we use is that we have minimally altered chondrule glass. And this is a very good example. And the other thing that we use are heterogeneous olivine compositions and pyroxene compositions. And so I've got a backscattered electron image of the same chondrule. And what you can see is in the olivines, they show difference in the backscattered contrast. You can see that there are lighter regions on the edges and darker gray regions in the middle. And these are differences in composition that have been preserved. They are pretty much in their original state after these chondrules form. So these are the kinds of things we use without being exhaustive on the criteria to identify very pristine meteorites. But how the matrix, that fine-grained material that's interstitial to the chondrules, behaves has not really been considered in any detail. And one of the reasons for that, it is so fine-grained and it's very challenging to study. We have to use special techniques to tease out that history. So I'm going to talk a little bit about matrix now, focusing in on it. And the point that's really important to take home is that matrix is exceptionally sensitive to record of nebular and asteroidal processes. And I've already mentioned one idea why that's the case. It's very fine-grained and it's a very complex mixture of materials. So matrix is the host of carbonaceous material, organic material, and it also contains what we call PreSolar grains. These are grains that are preserved from the giant molecular cloud collapse period of solar system formation. They were not processed within the protoplanetary disk. We also have silicate grains, oxides, and sulfides, and many other types. I'm not going to go through an exhaustive list. But as I've mentioned, this very unequilibrated assemblage responds very rapidly to thermal metamorphism or aqueous alteration. And so it's only in the very least altered, the minimally altered chondrites, that these primary characteristics of matrix are preserved. So what I want to do now is just introduce you to what are the characteristics of pristine CRchondrite matrix. And so this is work that we started doing in the mid-2000s, and my PhD student, Adrian, did a wonderful job of diving in and trying to tease out some of the details. This slide that I've just brought up here is a scanning electron microscope image, and it illustrates just how fine-grained the matrix is. This is matrix in QUE 99177, one of our very pristine CRchondrites. The scale bar here is the quarter of the width of the human hair, and you can see some grains in here that are micron sized, but you can also see there's a ground mass of gray material which we cannot resolve even at the SEM scale. It's submicron. So this is what I'm going to focus on now. And this is a little introduction to the characteristics of pristine chondrite matrix, and I'm going to show you some images of what this looks like. So going back to this X-ray map that I had up very early, one of my first slides, is to just remind you that the red material in here, so this is iron-rich matrix material, is all the interstitial stuff sitting between the chondrules that are green. That's what we're focusing on now. We have to use very high resolution imaging techniques like transmission electron microscopy, where we can get down to, now we can get down to the atomic scale in terms of imaging. And what I'm going to show you is that in these most pristine meteorites, the dominant component in all this red material is actually an amorphous iron-rich silicate. It is not crystalline. Crystalline, it has no ordering. It is completely structureless. Okay. I'm going to show you that there are abundant nanoparticles of iron nickel sulfides, and also very importantly, a high abundance of what we call oxygen isotopically anomalous PreSolar silicates. And these are grains which are extremely small. They are 300 nanometers in size or less, and are also commonly amorphous, though they can be crystalline. And one thing that's very important about the presence of these grains is that they are like the canary in the coal mine as far as alteration is concerned. Any significant alteration of these meteorites and these grains are destroyed. So the presence of them is a really wonderful indicator that we're looking at samples that have escaped any significant alteration. There's also olivines and pyroxenes. I'll show you examples of that. And we also find that we have variable development of hydrous phases, phyllosilicates. Now, one thing I want to mention here is these characteristics that I've listed here are only present in a very, very small number of meteorites. At the moment, there are probably only about 8 meteorites and that's including all chondrite groups, not just CRchondrites, that have these very pristine characteristics. So these are very rare and valuable objects, and we're always on the lookout for more in our meteorite collections to add to our understanding of these very early solar system processes. So just another little image to remind you of the very fine-grained characteristics, interstitial to chondria. So let's have a look at some of the characteristics of CRchondrite matrices. So I'm going to be showing you some transmission electron microscope images, which if you haven't seen before, look very bewildering. So I'll just try and lead you through some of the complexity, so at least you get a basic idea of what we're looking at. The first thing I want to say about CRchondrite matrices and pristine chondrite matrices is they are a mess. They're very complicated. And hopefully, if you look at this image, you'll get the idea, oh, yes, there's a lot going on. And so these are complicated to tease out what's going on. But the essentials are, in an image like this, the brighter grains are iron rich, and the darker grains tend to have a lower iron content. So the one thing I hope you can see is that we have brighter grains, which are dominantly sulfide grains that are distributed throughout the matrix. And they're also shown on the image on the right-hand side. All the bright grains in here are tiny sulfide grains that are about 100 nanometers or less. The medium gray material in here are silicates, and the AM means that they are amorphous, that they are structureless, okay? And there are patches of them, and they're intergrown with the sulfides in very complex ways. And then within all that mess, we have very fine-grained phyllosilicates. So I've indicated phyllo, so this region up here is a region of phyllosilicates, just sort of intermixed with the amorphous silicate and the sulfides. Now, you'll see that there are some very dark gray regions, and I've illustrated here, I put one that has OM on it. These are organic matter grains, and we're going to talk about those later, but these are distributed throughout the meteorite in all over the place. You'll see that organic matter is intimately associated with all these other materials. PreSolar silicate grain abundance. I mentioned that a little bit earlier. So this is a plot which shows the abundance of PreSolar silicates in parts per million in different meteorites. So we have the abundance in different chondrite groups. We have the CRchondrites up here, ungrouped in the middle, and the CRchondrites are down here. A high PreSolar grain abundance tells us that these meteorites have experienced minimal alteration. So when we started looking at the CRchondrites, we looked at two particular meteorites, QUE 99177 and MET 00426, which are shown here. And we suggested, based on their petrologic characteristics, that these were very pristine. And I mentioned pristine floss and tungsten at the beginning of my presentation. They jumped on that idea and they did surveys of matrix, and they came up with these very high abundances of PreSolar silicates, these tiny grains, these 300 nanometer grains. And so they agreed that based on our petrologic characteristics, these were very pristine meteorites. And at the time, the highest abundance had been found in this ungrouped carbonaceous chondrite, Aspero 94. But as you can see, QUE and MET have comparable, if not higher, PreSolar grain abundances than Aspero 94. And at the time, were the highest concentrations of PreSolar silicates. Since then, there's been a new meteorite DOM 08006, a CRchondrite, which has even higher abundances of PreSolar silicates. One thing I'd like to draw your attention to on this graph is that on Renazzo, which is the tight CRchondrite, has exceptionally low PreSolar silicate grain abundances, only 10 parts per million. So an order of magnitude lower than in QUE and MET. Okay, I'm going to talk about that a little bit later. This is a significant indication of what even moderately advanced aqueous alteration does to PreSolar silicates. And then also in the matrix, I got some more additional TEM images. We do have crystalline silicates. Outlined here are grains of olivine, forsterite, and enstatite, and there's another grain over here. And I have this wonderfully garish X-ray map, but the key thing that you need to know is that the pinks and the reds in here are little grains of olivine and pyroxene. And you can see the size here. This is half a micron, so these grains are 0.1, 0.2 microns in size. Everything we're looking at here is extremely fine grained. Okay. So these are the characteristics of pristine meteorites, but they may be pristine, but they're not completely pristine. And what makes us say that? I hate putting tables in presentations, so I've committed a crime here, which I apologize for. But this table is a table out of a very nice paper by Colin Alexander in 2013. And he measured the water content of a range of CRchondrites. And the water contents are shown here. And I'm just going to draw your attention to two, QUE9917, which is the meteorite I've been talking about, and Renatzo. And the water contents are 0.39 and 0.37. As I just showed you in that previous graph, the PreSolar grain abundances are much, much higher in QUE than Renatzo. So we have a meteorite which is as hydrated as one of the more hydrated meteorites, but still shows very pristine characteristics. So I'm going to focus a little bit on these two. So we have a dichotomy here posed by these pristine CRchondrites. The bulk water content is as high as one of the most highly altered CRchondrites. Actually, not the most highly, but one of the more altered CRchondrites, and Renatzo. Okay. The phases that are highly sensitive to alteration by aqueous fluids are preserved in this pristine chondrite QUE99177. It has amorphous iron-rich silicates, and it has a very high PreSolar grain abundance, and these are known to be highly sensitive to alteration. Here's that very elevated PreSolar grain abundance, and in Renatzo with the same water content, hardly any. We also find that the fine-grained silicates, olivine and pyroxene, show no sign of alteration as well. So the million-dollar question is here, where is this water, and why has it not modified all these very sensitive materials? So let's just have a look at that question. Okay. We went back and we revisited these two pristine meteorites, QUE9917 and MET00426. And this is another transmission electron microscope unit, very small scale, 0.2 of a micron. The sort of homogeneous looking material here is amorphous silicate. Okay? And what we found was that the amorphous silicate is being replaced by phyllosilicates. Phyllosilicates are clearly hydrous. Okay, so this makes a lot of sense. But when we look in the material here, what we find, and this is what's called a high resolution TEM images, these are lattice planes that are characteristic of phyllosilicate minerals, which are hydrated. They contain 10 to 15 weight % water. So we can reasonably make the argument that this material down in here is hydrated. But is the amount of alteration enough to explain the high water content that we see? Here's another example. The homogeneous looking regions that are outlined are amorphous silicate, and between them we have phyllosilicates. So we did an experiment. We said to ourselves, okay, one of the things that happens if you react an iron-bearing material with water is that water acts as an oxidant. And we should expect a signature of oxidation produced by dissociation of water and oxidizing iron 2+ in the amorphous silicate to produce iron 3+. And so we took these samples and we measured them on what's called a Stixon. I'll talk about this a little bit later. It's a way of looking at the X-ray absorption spectra for different elements. And what I'm showing here is an X-ray absorption spectra for the iron edge. And iron 2+ and iron 3+ absorb energy at different energies in an X-ray absorption near edge spectra, which is what we're showing here. So we have two peaks, one for iron 2+ and one for iron 3+. And what you'll notice is that the iron 3+ peak is much higher, telling us that most of the iron that's present in these amorphous silicates and in the phyllosilicates is present as iron 3+ in its most oxidized state. Okay. And so we measured both the amorphous silicates and the phyllosilicates. They have almost identical iron 2+ iron 3 ratios. Okay. They are highly oxidized. So the iron 3 plus to total iron ratio is around about 75%. Most of it is present as iron 2 plus. This is a very oxidized signature. It's much too oxidized to be a solar nebula signature. And so what we concluded from this is that it's indicative of hydration of the amorphous material, which caused oxidation of iron 2 plus to iron 3 plus. And so this is an indication that we may have hydration of the amorphous material. We subsequently measured the water content, and I won't bore you with the details of how we did that, but it's a very careful analytical transmission electron microscope technique that we use that accepts oxygen to reduce the amount of water. There are significant errors in it, but nevertheless, we came up with a value of about 10 weight percent water that's present within the amorphous silicates and also within the phyllosilicates. So we can say, okay, this material is probably not completely pristine. It has been hydrated and oxidized. So let's just summarize what I've talked about there in terms of these pristine meteorites. Even the most weakly CRchondrites that preserve some very pristine characteristics are hydrated. They have at least 10% water in them. We have argued that the amorphous iron-rich material is actually a hydrated, it's a gel-like material. Okay? So this is kind of the mud that I was talking about. And what we're seeing is that it has undergone partial transformation, a thermally driven transformation, recrystallization to form phyllosilicates. But despite that hydration, we have still preserved high PreSolar silicate grain abundances. And what we think has happened here is just this amorphous material is so reactive that it will basically suck up all the water and remove it from the system and prevent the PreSolar gains from reacting. So the conclusion that we came to is that despite this hydration, the least altered CRchondrites still preserve some very pristine solar nebula processes, and particularly the PreSolar grains. Having identified these meteorites based on this criteria, we can then ask the question, okay, they have organic material in them. What can we learn about the organic matter in these pristine meteorites that must be closest to some of the most pristine material that we find in the solar system? What do we know about carbon? Well, we know that carbon is dominantly present in the form of organic matter. We talked about that. This is the goo in my title, and so Carbonaceouschondrites are full of dark goo. I mentioned the fact that this is a high molecular weight insoluble organic matter. I'm going to call it IOM from now on. We call it insoluble because it's extracted from the meteorites by very aggressive dissolution by acids and oxidizing agents, and we're still left with this insoluble organic matter. Okay? And this material has affinities to terrestrial organic matter that we find in oil-bearing strata, for example, oil shales. And so comparable, we would call these kerogens if we were talking about a terrestrial rock. They're not exactly the same. There's some differences in their molecular structure, but that's about the closest terrestrial analog. The bulk structure of insoluble organic matter, its composition and isotopic composition is very well understood. There's been some wonderful work done by George Cody and colleagues at Carnegie Institute that has illustrated this. They've analyzed insoluble organic matter from all the different chondrite groups. And the CRchondrites have the most pristine and what we think is closest to the original primordial state of any insoluble organic matter in any chondrite group. And that's illustrated in this plot over on the right-hand side. This is the deuterium isotopic ratio of the organic matter, delta D, so it's relative to a standard. So these very elevated numbers indicate a very high deuterium content in the organic matter. The higher that value, the more pristine we think of the material as being, and then it's plotted against the hydrogen to carbon ratio. Okay? So higher hydrogen also indicates more pristine. The CRchondrites outlined in red here have elevated deuterium and also a high hydrogen to carbon ratio. distinct from the other carbonaceous chondrite groups, which fall down here in this range on this plot. So these are a great target for looking at. Now there are some caveats here. Although the knowledge of the bulk composition is really important, it is an average composition of all the grains which may be present, and there's very strong evidence that these grains may have considerable isotopic and compositional diversity. And over on my little slide here, over the pictures over on the right-hand side here, I'm illustrating that from the CRchondrite orgate, and these are nanosims isotopic images that allow us to look at the isotopic composition of organic grains in situ in the meteorite. And the scale bar here is 2 microns. So the resolution of the nanosims is somewhere around 100 nanometers. So what we're showing here on the left here is a carbon to silicon ratio plot, and the organic grains show up as these hotspots. So these are organic grains in the matrix of Auger. The same region over here, but the deuterium to hydrogen ratio. And so what you can see is this group organic grain here is very enriched in deuterium, but the other 3 grains that are here do not show up at all. Okay, so they have isotopically normal deuterium hydrogen ratios. So this tells us that we have heterogeneity in the oxygen isotopic composition. Now, this may be explained by mixing of grains from various distances from the sun or interstellar organic matter. That's a subject of debate. So what we've learned is the bulk composition doesn't give us any information on the spatial distribution of insoluble organic matter within the meteorites, the relationships of that matter to other solid phases, and small-scale compositional heterogeneities in isotopic or functional group chemistry. And so we have to combine a bunch of different techniques to tease that information out. So one of the things that's significant about organic matter in carbonaceous chondrites is that it is dominantly in the matrix. And these 2 plots are here to illustrate that there is this relationship between water and matrix abundance and carbon and matrix abundance. And so you can see when we plot the average data for the different carbonaceous chondrite groups, as the matrix abundance increases, so does the water content, and the same is also true of the carbon content. So water and carbon go together in the matrix of these meteorites, and we want to understand why that's the case. And so here are some of the questions that we're thinking about when we're talking about inorganic matter. What are the characteristics of individual organic matter grains in pristine carbonaceous chondrites? For example, is there isotopic, structural and composition heterogeneity? Are there mineralogical associations that could tell us how the organic matter grains formed and what their associations in the solar nebula were prior to accretion? Another question down here, is there evidence of relationships between aqueous alteration or organic material? And finally, do organics evolve with aqueous alteration? I talked about the fact that they may have reactions with water that affect their characteristics. Now, I'm not going to answer all these questions, but I'm just going to pick out some key points and show you a little bit of the characteristics of individual grains and their associations. So focusing mainly on those first 2 questions. How do we go about teasing out information about organic matter? Well, we want to do in situ analyses because we want to look at the material as is within the meteorites. So this is so much fun because we get to play with lots of different fancy analytical techniques, and we can coordinate them to get a wonderful picture of the characteristics of individual organic grains. And so the way we do this is we use a variety of different techniques, but we study what are called focused ion beam prepared samples. And these are samples that we cut out from our meteorite sample. It could be from a thin section, could be a little fragment, using an instrument like this. And so we pull out a little slice that's about 20 microns long and about 7 microns in depth and maybe about a micron or less in thickness. We can pull out grains that have been identified using the nanosims that might be isotopically anomalous. So we can start off by mapping our sample using nanosims and locate organic matter grains. We then cut them out with the fib. We then take that sample to a synchrotron. An example here, this is the Canadian light source in Saskatoon, and we do scanning transmission X-ray microscopy, or STXM for short. If you like acronyms, this is a wonderful game to play in. And so we do very high spatial resolution X-ray absorption near-edge spectroscopy. And what that gives us is functional group chemistry of organic matter grains. We can then take that same sample and take it to a transmission electron microscope, and we can image and get chemical analyses at the micron to nanometer scale of the grains. And so we can piece all this information together, isotopic composition, functional group chemistry, and texture and composition of the original grains to really understand the context. We're also developing techniques that we can do micro and nano infrared spectroscopy on these samples. And all of this work that is being done, not just by our group, but by other groups around the world, in the US and in Japan, is we're preparing to get the maximum science return from the Hayabusa 2 samples and the OSIRIS-Rex samples. Coming back shortly. So you've seen a TEM image like this already. This is my favorite Meteorite Que 99177. This is a fib sample. We've talked about the sulfides and so on in it, but what I want to illustrate is just how common and how tiny organic grains are. So what I've done is just outlined in red, probably about 50% of the organic grains that are present in the matrix of this meteorite. There are many, many more, but I just highlighted how they're randomly distributed. And if you look at the scale bar here, this is 1 micron, okay? So we're looking here at grains that are in the 0.1, 0.2 micron range, and they are distributed everywhere. So it almost doesn't matter where we cut a sample out from, we are going to see organic grains. And so this is a TEM image looking down at very fine scale. We can take that same sample to the synchrotron. And what I'm showing you over here is a STXM map. So this is a carbon distribution map obtained from STXM. So the bright spots in here are carbon-rich organic grains, and you can see they're everywhere, as I showed you in that earlier image. Now, I don't know if you can see it, but there's also a lower intensity blue material that's distributed between these larger grains. This is the kind of image that we get from X-ray absorption spectroscopy, but from our TEM image, which is shown over here, we can correlate exactly the grains that we identified as being carbon-rich in our TEM. And so we have two areas, area 1 and area 2 over here, in which we can look in detail at the association characteristics of the grains that we have identified. But one of the really important things that we can do with the X-ray absorption spectroscopy is that, for example, we can take a grain, this is a large organic grain, it's about 0.5 micron in size, and we can extract an absorption, carbon edge absorption spectra from it. And this squiggly line here is the carbon edge. And what you can see on here is that there are little peaks at different energies, X-ray absorption energies. And these peaks correspond to different functional groups in the organic matter. So we have aromatic C double bond here at about 285 EB. We have ketones at a little higher EB. And then we have carboxylic acid groups, which in this is just a little edge. It's not particularly a sharp peak. This is a very characteristic absorption spectra for organic matter grains in Carbonaceouschondrites. So if we take that and we analyze that area that I was showing you before, we can extract absorption spectra for, I've shown you two areas, 1 and 2. And so we've got two different curves from two different organic grains in green and in red. Particle 1 in red, particle 2. So particle 1 is from this region, particle 2 is from this region. And hopefully what you can see is that the spectra for these areas 1 and 2 are very similar. They have higher aromatic and ketone and a little bit of a carboxylic acid peak there, okay? But we have this weaker signal from the interstitial material here, and we have called this diffuse organic matter because it's present throughout the different material. And the X-ray absorption spectra for that material is shown here in gray, and you can see that it's characterized by much lower aromatics, but a much higher carboxylic acid, and also a carbonate peak. So there's two distinct types of organic material that we have identified: distinct organic matter grains with aromatic and ketone functional groups, and then our diffuse organic material, which is rich in carboxylic and carbonate functional groups. So very distinct. And this is a characteristic that we see in a suite of CRchondrites that we've looked at. I want to just focus just for a couple of minutes here to illustrate that there are spatial relationships between the organic matter and the silicates. And this is another TEM image. And I've highlighted a grain here, which is an organic matter grain. And located next to it is a much brighter grain. This is a grain of a mineral called Toshilinite that is it's an iron oxysulfide hydrate. It also has magnesium. It's very unusual, but does occur in chondritic meteorites. And it's indicative of relatively intense alteration, at least a higher degree of local alteration. And these grains we have seen tend to be associated with the largest organic matter grains. Okay? And so what this suggested to us was that organic matter, when it was originally accreted into these meteorites, was associated with water ice during the primary accretion of CRchondrites. I'm just going to show you another couple of examples here. This is another irregular shaped organic matter grain, and associated with it are larger, coarser grain Toshilinite. We are only looking at a two-dimensional slice here, so it's entirely possible that this grain is much bigger. Okay. We also have grain over here, organic matter grain, associated with more extensive alteration. We've got Toshilinite here, and amorphous silicates and phyllosilicates, which are hydrated. So this association between Toshilinite indicating a relatively high degree of alteration, at least locally in the matrix, is one that turns out to be very common. So let me just pull those different ideas together for this meteorite and talk about a sort of simple model that we came up with that sort of synthesizes these different observations. So I'm just going to start off with three nebular components. Amorphous silicate grains, which are just shown here in green, a little kitty-like representation. Sulfides in red, and organic grains, which could be isotopically normal or anomalous. And I've shown them coated in water ice. This is what these little lighter blue coatings in. So these are all grains that are free-floating in the protoplanetary disk, come together. So in our stage one, we are accreting this dust first, okay, into aggregates of all these three different components. These little fluffy objects then are accreted into asteroids. So we think of this as being our primary spatial association of organic matter, silicates, and sulfides. Asteroidal heating takes place, and as a consequence, we have stage two, where the water ice begins to melt. We have liquid water that migrates and hydrates the amorphous silicate. And we think this happens at very low temperature, only just above the melting point of water ice. And in that process, we oxidize the iron that's present in the amorphous silicate. So this little schematic is the idea that the water ice is melting and water is migrating out and surrounding the amorphous material. The extent of hydration that we see is variable within the matrix because it depends on the ice to organic matter silicate ratio, which may vary on a very localized scale. So then if we go to stage three, we begin to, as more advanced alteration takes place, we begin to form phyllosilicates and Toshilinite, nucleating next to the organic matter grain. So this would represent a Toshilinite grain. And this is probably because we have relatively high organic ice to organic matter ratio. And so that's promoting more intense alteration, at least locally. And then a final stage, stage 4 is, and I haven't really talked about this in detail, is that we have some redistribution of organic matter by aqueous fluids into cracks and veins, and formation of what we call nanoglobules. And so I've got a little picture here which shows sort of vein-like material of organics, which we think has been redistributed by fluids that have been migrating or evolved from these different materials. So just to summarize what we've learned from doing this coordinated analysis and wrapping this up, is that what we see is that organic grains are distributed everywhere through fine-grained matrix. And in fact, it doesn't really matter where you cut a sample, you find organic material, and it's present at the micron to nanometer scale. There are two different types of grains: discrete carbon-rich grains, which have this aromatic and ketone-rich signature, but we also have this diffuse organic material that is disseminated throughout the regions of silicate materials. And the functional group chemistry of these two types is distinct, but we think they may be complementary. And I haven't talked about it here, but what we see is that aqueous alteration leads to increased functional group heterogeneity in both these types of materials. All right, so just to wrap up then, what I hope I've shown you for analysis of organic materials is that when we take all these very powerful techniques and put them together and apply them to fib sections, we have this unparalleled characterization at the grain scale. We can look at isotopic composition from the nanosims work. We can look at functional group chemistry from X-ray absorption near spectroscopy, and then taking the TEM over here on the right-hand side is images of organic grains. We can look at the textural relationships to other phases. And so this is all information from the same 100 nanometer grain, so remarkable spatial resolution. And so from that, we gain insights into the possible origins of the grains and evolution of organic matter as a function of aqueous alteration. So my final slide here is really kind of a celebration of this incredibly exciting time that we have going on at the moment, where we have pristine, truly pristine samples of asteroids coming back. As I said, on December the 7th, if everything goes according to plan, Hayabusa 2 will return its capsule of pristine samples from asteroid Ryugu, and we will, after that 6 months curatorial activity, we will get to look at them. Now, these are going to be very complex. They are going to be carbonaceous chondrite materials with very diverse histories, and we're going to have to apply all these different techniques, coordinating microanalysis to obtain the maximum scientific return from these really precious samples. Ryugu may only return something like 100 milligrams of material. And so there's not going to be, but we hope there may be more than that, but it's going to be very fine grained. And so all these techniques that look at things at very fine scale are going to be very important. And so all that sample handling and analysis experience will be really invaluable for our next sample return from the carbonaceous asteroid in 2023 from asteroid Bennu. So that's going to be OSIRIS-Rex. So this is an incredibly exciting time for sample return science and developing the different techniques that we can use to analyze these materials. And I have a little picture of Bennu here just to remind us of the complexity of asteroidal materials. It's incredibly rocky and diverse material that is going to be brought back. And as far as we know, OSIRIS-Rex did an incredible job and collected a lot of material, probably tens of grams. It could be more than that. So with that, I'll wrap up and be very happy to answer any questions. And thank you all for coming this afternoon. It's been great.
Well done. You already have a lot of questions in the chat, so Alan and I can read those out to you now.
Great.
The first,
I was wondering if you could address the new classification of C1 versus C2. I know you're primarily C2, C3, in your talk today, but is it the composition of the interstitial material that is being looked at to differentiate these two classes?
Well, it's a great question. So the CRchondrites, are our holy grail for a variety of different reasons. They have the composition that is the closest to the solar photosphere. But there's an incredible paradox with the CIs, which are all type 1. Type 1 meaning that there's essentially no primary solar nebula material present. Everything is of a secondary origin. So phyllosilicates, carbonates, for example, are the dominant, and iron oxides, hydrated iron oxides, are the dominant material that are present. But despite this very significant hydration of the CI chondrites, they have this remarkably pristine chemical composition. So the type 1s, there are two different things. The I really stands for the chemical characterization and also the oxygen isotopic composition of the different groups. But the 1 describes the amount of alteration. So we can also have CM1 chondrites that have a distinct chemical composition from the CIs. They're very pristine, but they're a little more fractionated in their volatile element composition. They're not as enriched and volatile as the CIs. But we have examples that are of CMs that are also completely altered, and we call those type 1s as well. And the same is true for the CRs, but there's only a I think there's actually only one type 1 CR chondrite.
Thank you.
Hey, Juliet, why don't you read some of the questions in the chat?
Yeah.
Yes, that's what I will do now. The first would be, do the CV3s also contain the Fe-rich silicates? Please.
Great question. All the CV3 chondrites that we have been either heated or modified more extensively by aqueous alteration. They also have lower PreSolar silicate grain abundances. And so the CVs are both groups that oxidize and reduced are more processed than the most pristine CR chondrites. So no, they don't contain these amorphous silicates. They have been recrystallized either in the absence of fluid, I wouldn't say in the absence of fluids, but under drier conditions, or they have been hydrated much more extensively. So these very pristine materials have all been destroyed. So at the moment, we do not have a pristine CV chondrite in our collection. It'd be great if somebody could find one.
And a follow-up question, have you considered that the water could be hydrogen bonded to its source, a polymer that produced the water at its formation?
Yeah, that's also a possibility. Yes, I mean, that's something that needs to be explored in more detail. There's obviously, I think, a significant amount of water around. So I think it's reasonable to assume that most of it is present as water ice, but yes, there could be other forms, certainly. It's something that still needs to be addressed.
How heterogeneous is the water content in matrix material?
Well, that's something we're still trying to come to terms with, because we don't really have very precise analytical techniques to do it. The technique that I showed you has large error bars on it. It's very challenging to do. And what it's based on is doing an analysis and measuring all the elements that are present and the oxygen content as precisely as you can. That's very difficult to do in a TEM. It's very time consuming. And what we do is assume that oxygen is combined stoichiometrically with the other metals. And then any excess oxygen we then assign to water. And we can't measure hydrogen, we can only measure oxygen. So this makes it a rather indirect way of doing it. And so for each determination, we have an error of probably at least 3 or 4 weight percent H2O, okay? And so we have to do a lot of measurements to convince ourselves that yes, we are actually detecting water. This is where being able to do nano-infrared spectroscopy on our same samples will be really helpful. But that's really difficult to do. Water absorbs very easily to the high surface area of these samples. And so unless we can be sure we've got we haven't got any absorbed water, we have a little bit of an issue. We would probably need to do them under vacuum, and we're not there yet with being able to correlate infrared measurements with samples measured using the TEM technique that I was talking about. So a long way to go. It's a great question. So the heterogeneity, we certainly think we see heterogeneity, but quantifying it at this point, we still have work to do. But I think it will happen. We have to be persistent.
Thank you. And then the next question be, when you cut out the samples via FIB, how do you protect the organic matter from heat? Is this cryo FIB?
Oh, great question. Yes, this is something that has been a big concern to us about whether FIB sample preparation damages the organic material. So the way we addressed that is we took samples of very well characterized terrestrial kerogens. They're like standards. They're as close as possible to the organic matter that we have in chondrites. And we prepared FIB samples under different conditions. And then we did the X-ray absorption near-edge spectroscopy. We took crushed grains that had never been near a FIB, and we took our FIB samples and we measured what the functional group chemistry looked like and the hydrogen isotopic composition using nanosims on both kinds of samples. And what we found was that there is absolutely no distinguishable difference between the FIB prepared samples and the samples which had never been anywhere near a FIB. What we do know is a problem, though, is it's not actually the ion beam cutting, but it's actually the electron beam imaging. So we're looking at these samples when we're imaging when we're using SEM. And we know that that really can mess up the functional group chemistry. And so what we do is we have to image, we do it at extremely low accelerating voltage in the SEM and very, very low beam current, just a few picoamps. From the work that we've done, we can demonstrate very clearly that we are having no effect on the organic material from our sample preparation procedures. It's a great question. It was something that we were really concerned about when we started doing this, that we could be modifying the organic material by our sample prep. So we wanted to be absolutely sure that we are really preserving exactly what we had in the sample, in our sample prep. And I think we've done that about as good a job as we could possibly do.
I'd like to interject a question of my own. It's easy to imagine that you're accreting ice in the carbonaceous chondrites beyond the snow line, but we have aqueously altered ordinary chondrites, of course, which lack Toshilinite. What do you think the source of water is for those, since ice wouldn't persist long in the inner solar system?
Well, now you're going to kill me here, Alan, right? You want me to speculate wildly. I suspect that, we don't know that the ordinary chondrites accreted within the snow line. So I suspect that we had similar types of water ice grains that accreted with the ordinary chondrites as well. Interesting, I didn't talk about it here, but we've recently found regions of semicona that look exactly like these pristine CRchondrites in terms of their characteristics. They have organic material preserved in them. They have amorphous silicates. And so I think there could have been migration of material from the inner part of the solar system outwards. And so we don't know the ordinary chondrites accreted in the inner solar system. We do know most of the material probably formed in the inner solar system. But I think there has to be, I think it's quite possible the water, ice, and organics are actually an outer solar system component that was added in.
Okay, Juliet, go ahead.
Yes, we have 4 more questions. The first being, why are there grains of organic matter as opposed to it being more finely distributed within the matrix, i.e. no grains at all? Did the grains grow? Are they fragments of larger pieces of organic matter that were distributed?
That's a great question. I haven't talked about what we've done on CM chondrites, but in the CM chondrites, we find very distinct coatings of organic grains on different types of mineral grains, for example, what I think were once iron carbides. I personally think that we had a huge range of organic grains that may have been synthesized, for example, on the top of ice grains as coatings on ice grains. So I think the primordial distribution of grain sizes was probably very variable. So I don't think the smallest grains are fragments. The larger grains, great question, is that grain growth. This is an issue that we're arguing backwards and forwards about. What is the effect of water on the characteristics of primordial or the original grain size? What we do know is that if we look at the most heavily altered CRchondrites, the distribution of organic grains is completely different from what I was showing you in these samples. So we do know that fluids certainly modified the characteristics of organic, and the organics are clearly mobile and they change in character. What we haven't got a hand on yet is how much they've been modified in, I'm going to call these very pristine chondrites. I think there are clearly areas where in the matrix where they have been extensively modified, because we find these vein-like structures, which clearly had to form at some later stage after all the material came together. That's something that needs a lot more work to do, because it needs a lot more fib samples prepared and look at the statistics and the distribution of different grains. So I don't have a definitive answer to that question. It's a great one. What I can say is that I do believe that certainly there's evidence of modification of some of the organic grains from their original primordial characteristics. I think we always have to keep in mind that whatever mixture of materials was present in those meteorites to begin with, we're now looking at a rock, right? And that rock has undergone processes, and maybe that's minimal, but because the organics are probably so reactive, I don't think the chemistry is exactly like it was in its primordial state, but it's about as close as we can get. Maybe we'll get some other samples that show even less alteration. I hope, right? Maybe they'll come from Hayabusa 2 or from OSIRIS-Rex. I'm keeping my fingers crossed.
The next question is, can you assume that the samples of materials taken from the surface of the asteroids is indicative of the interior composition given exposure to sunlight and radiation?
Yeah, that's a really great question. Yeah, that's the $1 million question. What we think we see from the camera that was on Hayabusa 2, from the Scout rover, is that there are chunks of rock that look like carbonaceouschondrites. You know, they are centimeters in size. Now, if we bring a chunk like that back, I think we can probably be reasonably confident that these are lithified objects, and the interior of them is going to look like a carbonaceous chondrite that we have on Earth. But the finer dust-like material from the surface, I think, will almost certainly be modified by regolith processes. So we have this phenomenon called space weathering that, you know, we have obviously high energy particles that are bombarding the surface. We have micrometeorite impact. Those processes can modify the surfaces of grains, they can amorphize them. So certainly the smaller grains, this is what we will find out, how much they have been modified. And it could, not only will it be the silicates, it could be the organic grains. But I think regolith processes are so complex that we will have a mixture of regolith mixing, that we will have a mixture of material that is relatively pristine in that finer grain component, and stuff that really might be quite heavily modified. But I think the larger fragments, who knows? I'm hoping we have pieces that maybe a centimeter in size are going to be more like our Carbonaceouschondrite samples. I'm really hoping we haven't gone all the way to these asteroids to bring back a piece of sample that looks exactly like a CM-chondrite. I would love it to be something different.
I think we can be assured it'll be something different, Adrian.
I believe so, Alan, yes. Yes, I'm very confident that's going to be the case.
So, Juliet, let's take Caitlin's question next.
Okay. I'd love to hear a little more about the carbonate signatures in the diffuse organics. Can we distinguish whether the CO3 is a functional group within the OM or coming from finely intergrown small carbonate minerals?
That is a fantastic question, and thank you for asking it.
I saw the phrase carbonate was like, oh, what?
Yeah, well, it's a great question, Caitlin, and we don't know the answer to that yet. Okay, if it's individual carbonates, they are so small that I can't resolve them. However, I'm getting this fancy new TM that we're installing at the moment that I think we should be able to answer that question. At the moment, I think the carbonate groups are actually in the organics rather than being discrete grains, but I'm quite happy to be proven to be wrong on that one. So yeah, I mean, it'd be a very interesting question. And
yeah, either would be really, really interesting.
Yeah, absolutely, because it may be that some of these groups are actually forming the carbonates that you're looking at.
Exactly my thinking.
Yeah, and one of the things that has shown up, and I didn't talk about it, is that in the X-ray absorption near-edge spectroscopy, we do find distinct carbonate grains, and they are really small. They're like 100 nanometers in size, which surprised me. I was not expecting to find that, but they are around.
And so in what sort of class of meteorites? This is like a CR?
These are in the CRs, yes. Yeah,
okay.
Yeah. So, we think of most of the carbonates as being bigger, but there's population of very small ones that we...
Well, and in these most pristine ones that you're studying, we don't usually see the big carbonates either.
Right, exactly.
So it could just have not enough alteration to mobilize enough calcium.
Right, I mean, and it may be that the carbonate that we're seeing this diffuse may be the earliest stages.
Yeah, that was my thought. I was super curious to know about them.
Oh, it's a great question. It may be the case. I don't know the answer yet, but maybe in a year's time.
Cool.
Ming Shan wants to know where the CRchondrites accreted, and do they accrete close to comets?
Well, that's a great question. We want it to be in the Oort cloud. I'm thinking outer solar system, but not as far out as comets. I don't think there's any reason to think they accreted so far out. And I don't think the D to H ratios are consistent. So yeah, I would say inner part of the outer solar system.
No, I would agree, Adrian. I mean, there's so many similarities and continua of petrologic properties among the carbonaceous chondrite groups. There's no reason to expect that they'd be far away from all the others.
Oh, right. I think I would agree with that. Yeah, absolutely.
Okay, well, we have one final question that we will entertain. And Juliet, you can read it. It's from Peter Utas.
Do we know whether the material from Bennu is type 3 material, i.e. pristine in that sense, or is it pristine in the sense that is gathered freshly? No entry Earth state issues.
Yeah, no, that's a great question. Yes, pristine in the sense that it has not been modified by entry into the Earth's atmosphere. What we think at this point is that both Ryugu and Bennu are probably somewhat metamorphosed carbonaceous chondrites. That's the indication at the moment based on analog studies from spectroscopy of heated carbonaceous chondrites done in the lab on Earth and comparing those spectra with the spectra from both the OSIRIS-Rex and the Hayabusa 2 spacecraft. They seem to match moderately, well, okay, I would say mildly metamorphosed carbonaceous chondrites. So they're pristine in the sense that we have regular samples. But if we just looking at the images that we're seeing from the surfaces, there's clearly heterogeneity there. So I expect a mixture of materials. I expect to see some material that has experienced some metamorphism, and some which may be less affected by metamorphism and aqueous alteration. So I think, we're going to have, a grab bag of different samples, which is going to make them really interesting to study.
Okay, I think that should wrap it up. I want to thank Adrian very much for his wonderful, stimulating talk of all these really great images and all the fine work, and I mean that in two different senses of the word, that you're doing, and we really appreciate it. And I want to thank everybody for attending the lecture, and we will have a recorded lecture that I made on the origin of chondrules that'll be posted December 1st. And we will start again with live lectures in January. And Juliet will send out notices of all those things. So again, let's thank Adrian very much. And the meeting is concluded. Again,